Most entry-level audio guides tell you that file formats don't really matter and that balanced cables just make things louder. But accepting that oversimplified advice is a guaranteed way to bottleneck your entire system. As an audio engineer, I can tell you that building a true high-fidelity setup requires mastering 4 specific stages: controlling your audio source, prioritizing the analog output stage of your DAC, matching your amplifier's power synergy, and understanding the true physics of balanced connections. If you don't understand how these 4 stages interact before you start swiping your credit card, you will end up wasting thousands of dollars on high-end gear that actively fight against itself. Today, we are cutting through the confusion for anyone looking to build or upgrade their audio system. To stop you from wasting your money, we have to first understand your signal chain. The signal chain is simply the chronological path of electrical audio signal traveling from its origin point all the way until it physically reaches your ears. In a high-end audiophile setup, this usually starts with a digital source. This could be a dedicated network streamer, your laptop, your smartphone, or a CD transport. That source sends digital data, raw ones and zeros, into a standalone digital-to-analog converter or a DAC. The DAC's entire job is to translate that digital code into an analog electrical signal. From there, that analog signal travels into a preamplifier, then an amplifier or an integrated amp, and then it gives power. Finally, that amplified signal moves through your cables into acoustic drivers of your speakers or headphones. If there is a weak link anywhere in this chain, it does not matter how much money you spend on the rest of the gear. You could have a $5,000 pair of headphones or speakers, but if you are feeding them a poorly converted electrical noisy signal from a bad source, they are just going to accurately reproduce that noise. We are focusing specifically on these 4 core parts today because they are the most misunderstood aspects of the chain, and getting them right is an absolute foundation of any great system. The first step in your signal chain is the source, and this is where you need to understand the reality of sample rates and bit depths before relying solely on streaming services. There is a popular narrative out there right now that file formats basically don't matter. You will hear people claim that a 320 kilobit MP3 is essentially identical to a high-resolution, lossless file, and that 95% of audio quality simply comes down to how the track was mastered at the studio. Now, half of that is true. Mastering is absolutely critical, but the idea that file resolution doesn't matter is fundamentally flawed. We have to demystify high-res audio. When you look at a digital file, you will see a sample rate like 44.1 kilohertz or 192 kilohertz. That number dictates exactly how many times per second the original analog sound wave was captured or sampled during the digital conversion. A 192 kilohertz file is taking 192,000 snapshots of audio every single second. The higher the sample rate, the more accurate your equipment can reconstruct the smooth, continuous analog wave of the original performance. Then you have bit depth. Typically 16-bit or 24-bit. Bit depths dictate the dynamic range and the noise floor of the recording. A 24-bit file gives the audio vastly more room to breathe. It allows for absolute dead silent backgrounds during quiet acoustical passages while still having the headroom for massive, explosive, orchestral crescendos without distorting. To be incredibly clear, streaming does not ruin audio quality. Platforms like Qobuz and Tidal provide fantastic high-resolution streams that I myself listen to. However, convenience always costs you control. When you stream music, you are at the mercy of algorithms and network bandwidth. If your cellular connection drops, the streaming service might dramatically compress your high-resolution file down to a low bitrate stream to keep the music playing without buffering. More importantly, you have zero control over which specific master the algorithm decides to serve you. The record label can take a beautifully dynamic original studio master from the 1980s and quietly swap it out overnight for a heavily compressed, incredibly loud modern remaster, and you would have absolutely no say in the matter. If you want absolute baseline fidelity, buy offline lossless files or physical media. By storing high-resolution files locally on a hard drive or a spinning disk, you guarantee that you are passing an undiluted, bit-perfect signal into the very next link of your signal chain. You are putting the control of the mastering back into your own hands. Now, moving down the chain, we reach the digital to analog converter, or the DAC. If you want to stop wasting money, you need to stop obsessing over the specific digital silicon chip that's inside that box. The DAC's job in the signal chain is exactly what it sounds like. It translates those digital ones and zeros from your source into a continuous analog electrical signal. Where buyers start researching DACs, they inevitably fall down a rabbit hole of forum debates. People hyperfixate on whether a unit uses a ESS Sabre chip, an AKM chip, a Burr Brown chip, FPGA, etc., etc. They treat the silicon as if it's the only thing dictating the sound profile of the unit. However, as an audio engineer, I can promise you that the power supply and the analog output stage of the unit matter significantly more than the brand name stamped on the silicon chip. Here's why. The actual DAC chip simply does the math. It decodes the digital file, but the electrical signal that comes directly out of that chip is incredibly tiny, fragile, full of high-frequency digital noise. It cannot be sent directly to your amplifier. It has to pass through the DAC's analog output stage. The analog output stage is a physical circuit made up of operational amplifiers, capacitors, and resistors. Its job is to filter out the digital noise and amplify that tiny signal up to a standard line level voltage. This is where the actual tone, warmth, and soundstage of a unit are born. If a manufacturer buys a brilliant top-of-the-line ESS Sabre flagship chip, but pairs it with a cheap, poorly engineered analog output stage made with budget capacitors, the resulting sound is going to be harsh, thin, and fatiguing to listen to. Furthermore, you have to consider the power supply. Audio signals are just modulated electrical currents. If the power supply feeding the DAC is noisy or poorly isolated, that electrical noise physically bleeds into your audio signal. When you're researching DACs, do not just look at the digital spec sheet. A great DAC is a holistic piece of engineering. Look at the chassis build quality, look at how they isolated the digital circuitry from the analog circuitry, look at whether they are using a robust linear power supply, prioritize the analog engineering, and the digital math will take care of itself. Once we have a clean analog signal, it needs power. It moves into the amplifier. The biggest mistake you can make at this stage of the signal chain is assuming that more power automatically equals better sound, and just buying the most powerful unit that you can afford. Amplification is not just about volume. It is about synergy, impedance, and sensitivity. You have to match your amplifier to the specific electrical demands of your headphones, in-ear monitors, or speakers. Let's look at impedance and sensitivity. Impedance, measured in ohms, is essentially how much electrical resistance your headphone drivers or your speakers put up against that amplifier. Sensitivity, measured in decibels per milliwatt, tells you how efficient the headphones or speakers convert that electrical power into actual acoustical volume. Let's say you own a pair of high-end in-ear monitors. Modern IEMs typically have low impedance and incredibly high sensitivity. They are extremely easy to drive. You could run them off of a potato if you wired it correctly. If you take those high-sensitive IEMs and plug them into a massive $3,000 desktop amplifier designed to push huge amounts of current, you have a massive synergy mismatch. You are going to introduce a terrible background hiss into your signal chain because your amplifier's noise floor is too high for such a sensitive driver. You spend thousands of dollars to actively make your music sound worse. Conversely, let's look at the other extreme. Say you buy a demanding low-sensitive planar magnetic headphone like the Hi-Fi Man Susvara. This is a dog to drive. If you plug them into a basic phone dongle, it might technically produce some sound, but it will sound hollow, thin, lifeless, and you'll have no volume. It lacks the electrical headroom required for dynamic volume swings. When the music calls for a massive bass drop, the dongle simply cannot supply the current fast enough, and the audio clips and flattens out. The key here is that a quality dongle DAC is actually perfectly adequate for a vast majority of headphones on the market today. If you can hit comfortable listening volumes without maxing out the volume slider on your device, and you don't hear any background hiss or distortion, your current amplification is doing its job. Look at the impedance and sensitivity of your transducers before buying an amp. Test with what you have already. Only spend money on a dedicated amplifier when you legitimately cannot reach clean, comfortable listening volumes, and when you specifically need practical features like input switching or a physical volume knob. Balance your connections. This brings us to the final step in the signal chain, the cables and connections that physically deliver the power to your headphones or speakers or other equipment. We need to talk about balanced versus unbalanced connections. If you spend any time researching audio gear, you will see a lot of hype around the new 4.4 millimeter or XLR balanced cables. But there is a very common, very frustrating myth circulating online that balanced connections magically improve the sound quality simply because they deliver higher volume. This completely misunderstands the physics of why balanced geometry was invented. Balanced connections do not exist just to make your music louder. They were engineered for a very specific physics purpose: to reject electrical noise and preserve the purity of the signal chain. A standard unbalanced headphone cable, like the typical 3.5 millimeter jack on a pair of consumer headphones, uses 3 contact points. It has a left audio channel, a right audio channel, and they both share a single common ground wire. Because the ground is shared, there is a physical opportunity for the left and right channels to bleed into each other, which slightly reduces the width of your stereo imaging. More importantly, standard cables can act like antennas. As the audio signal travels down the wire, it can pick up electromagnetic interference from your Wi-Fi router, your computer monitor, or power cables running behind your desk. A balanced cable completely redesigns this architecture. Instead of 3 contact points on that headphone cable, a balanced connection uses at least 4. In the case of XLR interconnects, we're using 3 on each side, so a total of 6. The left channel gets its own dedicated positive and negative wire, and the right channel gets its own dedicated positive and negative wire. As well, we have what's called a send and receive signal, a hot and a cold. There is no shared ground. This immediately improves channel separation, giving you a wider, more precise soundstage. But the real magic is how it handles noise. In balanced systems, the amplifier sends 2 identical copies of the audio signal down the cable for each channel. I talked about send and receive, but it flips the phase of one of those copies completely upside down. As those 2 signals travel down the cable, they inevitably pick up the same electrical interference from your room. But when those signals reach the end of the line, the equipment flips that inverted signal right side up and recombines them. Because the noise they picked up along the way is identical, flipping the phase of the audio effectively flips the phase of the noise, causing it to mathematically cancel itself out. This is a concept called common mode rejection. It physically deletes the electrical interference from your signal chain. So yes, balanced outputs often provide more overall voltage, which results in more volume, but that is a byproduct. The true benefit is the drastically lowered noise floor, the elimination of ground loops, and the completely silent background. However, you should only invest in balanced cable if your DAC and your amplifier actually feature true differential balanced circuitry inside the chassis. If your gear isn't truly balanced internally, a balanced cable won't do anything for you. Building an incredible audio system isn't about buying the most expensive individual pieces you can find. It's about understanding the physics of your gear and ensuring that every single step in your signal chain perfectly complements the next. If this guide helped clear up the confusion and demystify the audio market for you, make sure to hit that subscribe button down below for more no-nonsense engineering advice. Now that you understand the signal chain, you might be wondering if you actually need a dedicated amplifier for your new headphones. The truth is, you might not. I made a video breaking down exactly when you need an amplifier and when a simple dongle is perfectly adequate. Click the video on your screen right now and we'll see you in the next one.